All right, so good afternoon, everyone. Thanks for joining the GLASE Webinar Series. Today, we're going to be listening from Erik, Runkle, Dr. Erik Runkle, and Roberto Lopez from Michigan State University on supplemental greenhouse lighting during propagation. The GLASE Webinar Series features the latest technology innovations and best practices in the controlled environmental agriculture industry, providing the participants an opportunity to discover new solutions and to connect with industry experts. Dr. Erik Runkle is a professor and extension specialist in the Department of Horticulture at Michigan State University. Erik obtained a bachelor's degree in ornamental horticulture from University of Illinois and his master's and PhD in horticulture at Michigan State University. Since he joined the faculty in 2001, he and his graduate research team have performed numerous practical experiments in controlled environments to determine the effects of light, temperature, and other environmental factors on plant growth and development. His co-speaker today, Dr. Roberto Lopez, is an assistant professor in the Department of Horticulture at Michigan State University. Roberto earned his master's degree in 2003 and PhD in 2007 from Michigan State University. In 2008 until 2016, he was assistant and then associate professor in horticulture and landscape architecture at Purdue University. His research focus is on energy efficient propagation and production of floriculture crops with an emphasis on lighting and temperature management. By controlling environmental factors such as light, temperature, and carbon dioxide, Roberto has been able to influence crop timing, quality, flavor, nutrition, and color in many crops. A recorded version of this webinar will be available at our website at www.glaze.org, where you can find also, and you can also find and register for the next webinars in this series. If you have any questions about the presentation today, please submit your inquiries using the Q&A button. We will do our best to answer all the questions at the end of this presentation. So now, with no further ado, I would like to thank our presenters and pass the word to Erik and Roberto. Erik, thanks.
All right, thanks, Eriko. Appreciate the opportunity to share some of the research that we have been doing over the last 10 years or so. And we talk about supplemental greenhouse lighting. When we talk about lighting in general, there are a lot of compelling reasons to increase the daily light integral. And so Roberto and I are going to talk about basically showing some of the merits of including supplemental lighting, talk about installations, and then toward the end, we will talk about considerations when you're selecting between a HPS or a high pressure sodium fixture and LEDs. And that's probably one of the more common questions that we get. So Roberto and I will go back and forth a few times as we go through our presentation over the next 35 or 40 minutes. Okay, so just a few definitions. One is first and foremost the daily light integral, acronym commonly used as DLI. And this describes the cumulative number of photosynthetic photons delivered in a region from 400 to 700 nanometers. So it includes colors of photons that are blue, green, red, and then the colors in between. It's the number of photons that fall within a 1 square meter area, which is almost 11 square feet. And an analogy that's often used is comparing it to a rain gauge, where when we're measuring rainfall, we're usually not interested in how much rain we're receiving per second. We're actually more interested in how much is accumulated over the course of a day. And so that's really what the daily light integral is the cumulative amount of photosynthetic light received per day. You will see a few questions that will be popping up during your presentation. We're just simply interested in knowing what kind of audience that we're talking to. So I think actually we just have a couple questions. So we appreciate your input on that. So daily light integral varies considerably in a greenhouse scenario. So among the factors that influence that are the time of year, of course, that influences the angle of the sun and its incidence on your facility. the location of where you are, how much cloud cover you typically receive. So we are in Michigan, and we get a lot of winter cloudy weather from Lake Michigan. And so we have quite low daily light integrals during the winter. Of course, the time of year also influences the day length, and so we enjoy long photo periods this time of year and quite short ones during the winter. The glazing structure, the glazing and the structure, so what type of glazing material is there, how old is that material, how many layers are there, as well as whether there are any curtains that are used. The structure and the number of obstructions overhead, whether there are hanging baskets placed overhead, which is quite common when we're growing ornamental plants in the spring. And then really the only way to increase the daylight integral, other than minimizing shading and obstructions, is to add supplemental light from electric fixtures. Jim Faust developed these daily light integral maps. And these are maps that have been out for about a year now. They're revised from ones that he originally produced probably 15 years ago. These are developed in part through support from the American Floral Endowment, and these maps can be downloaded in an interactive way using the URL at the bottom. And so as you can see, this is for the outdoor daily light integral. The unit we use is moles of photons per square meter and day, and these are average values for the month of January. So you can look at your location and month and get a pretty good estimate of what the outdoor light integral is in your area. The challenge then is to translate that information to how much light you're receiving in a greenhouse or in your growing environment. And so the best thing to do is to try to quantify what is the light transmission inside your greenhouse. And that can be done on a clear summer day, preferably, or actually just any sort of clear day when you don't have clouds, but maybe around solar noon, where you take a quantum sensor, or actually in this case, a foot candle meter would read just fine. Take a measurement outside without any obstructions, and then immediately go in your facility, take a few measurements, and then determine how much of that light is getting through your greenhouse. Oftentimes the value is about 50 to 60% of the light is getting through your greenhouse. The rest is somehow blocked or is reflected off of your glazing material. So this is a map for the month of July. Of course, as we go into February, we're starting a period where the days are increasingly getting long, and the angle of the sun is moving a little more towards the south. And so the increased light integral is the result. So you can see in Michigan and in many regions of the northern third of the United States, an average light integral in this case would be 15 to 20 moles outdoors, whereas inside we might be looking at 7 to 10 moles. Then once we get into March, for many growers, we are experiencing conditions that we typically see are not light limiting. And so we're typically getting about 10 or 12 moles per day or higher. And of course, much higher than that in the deep south and the southwestern United States. So why is this important? Well, there are many reasons or benefits to providing and giving ample light to plants. Among them are that the plants under higher light typically have smaller and thicker leaves. They have more and larger flowers when they do flower. They have greater branching and thicker stems, a greater amount of root growth, and this is especially important for plugs and cuttings. When we're growing plants that have a harvestable yield, like maybe a lettuce or a tomato, that typically increases with light. And then when we're talking about ornamental plants, we are interested in time to flower, and we find, and others have reported, that plants simply flower quicker under a high daily light integral. So there are three main horticultural lighting applications that we talk about, and it's important that we don't confuse them, and we do see a fair amount of confusion when we do visit growers. So the first type is photoperiodic lighting. This would be what we might call mum lighting. This is the delivery of low intensity lighting only at night, and it's provided to regulate flowering of plants that are sensitive to photoperiod. So probably the most common example would be to install mum lighting to mums to prevent flowering, or similarly low intensity quantities of light to promote flowering of long day plants. So again, the key is that this is low intensity, typically 1 to 2 micromoles. In contrast, supplemental lighting intensity is going to be much higher, and this is done specifically to increase photosynthesis and therefore plant growth. And then finally is sole source or indoor lighting, and this is where basically the only amount of light available to plants is from the electronic fixtures. This is a chart that basically compares these 3 types of horticultural lighting applications. I won't go through all of this, but just to highlight the supplemental lighting in the middle, typically it's delivered only in greenhouses. We see that it increases growth, the harvestable yield, and the plant quality attributes. So in other words, we often get a higher quality plant, or the plant finishes earlier under higher light. We commonly see it with young plant production, and hence the topic today, but sometimes in other high value crops in which we can get an economic benefit from adding additional light. Typical intensities vary quite a bit, but for ornamental plants, it's typically 60 to 100 micromoles per square meter in second, and it would be roughly twice that, or maybe even more, for fruiting vegetables. Common lamp types are high pressure sodium, but more and more we're seeing red and blue or red and white LEDs in a fixture. The lamps are operated at night or on cloudy days from spring to fall. There is no benefit to running fixtures on a sunny day in the summer. They typically operate for up to 20 hours a day. And then when we compare them to other types of fixtures, we would say that they have relatively little impact on influencing the shape or the architecture of a plant. In contrast to sole source lighting, the light quality of the fixture has a much more pronounced effect on the architecture of the plant. So with that, I will now turn the talk over to Roberto.
Okay. Well, good afternoon, everyone. So basically, I'm going to now talk about work that we've conducted with supplemental lighting during liner production. Most of our work has focused on herbaceous annuals and perennials. However, in the next few weeks, we're actually going to start some work on culinary herbs. So hopefully in the future, we'll be able to share that information. Erik, can you go to the next slide, please? So those of you that are located in northern latitudes probably can relate to this photograph where during peak propagation of unrooted cuttings, this is typically what the weather is like outdoors. And obviously, if you're a propagator of young plants, you want to minimize that production time, whether you're rooting cuttings or you're producing plugs. And obviously, you want to reduce your energy costs and produce the highest quality plug or liner. However, when we have these sorts of environments, it can be quite challenging. Oftentimes, when we begin this work, we would talk to growers, and their main concern was maintaining that temperature. We would often ask, what is the daily light integral during propagation? And most had no idea or weren't tracking that. And it would take them anywhere from 6 to 7 weeks to root a crop like New Guinean patience. Next slide. So during young plant production, the daily light integral outdoors, and this is for northern latitudes, obviously as you move further south, that daily light integral is going to increase. But for northern latitudes, it's anywhere from 5 to 20 moles per day. As Erik indicated, once you move within a greenhouse structure, your light levels can be 50% or less that of outdoors because of the many factors that he included or talked about. Therefore, we have found that the DLI during young plant production, especially during peak propagation in February, can be anywhere from 2 to 5 moles, even lower during extended periods of cloudy weather. So folks in closer to Lake Michigan, in Michigan, often find that they can have DLIs as low as 1 mole per day, so very, very low. Next slide. So here's some of our recommendations when using supplemental lighting. You can provide anywhere from 50 to 70 micromoles of photosynthetically active radiation from either high pressure sodium lamps or LEDs. And we're actually finding that some growers are going up to about 120 micromoles. Obviously, it's going to be dependent on your structure as well as the supplemental lighting that you're utilizing. So this is during stage 1 to 2, basically from when those cuttings are stuck until when you begin to see callus formation. So you want to try to target a daily light integral of anywhere from 4 to 5 moles during this time period. Also, very important to note that you want to provide indirect or diffuse light. So this is primarily from the sun by utilizing shade curtains or whitewash to maintain a photosynthetic photon flux density of anywhere between 100 and 200 micromoles. Now, as we move on to stage 3, which is root development, we're going to obviously increase our light intensity. So if you're providing supplemental lighting, anywhere from 70 to 120 micromoles of light, with a target of anywhere from 8 to 12 moles per day. Once those roots have initiated, you're going to want to obviously increase that total photosynthetic photon flux density between 200 to 400 micromoles. And then during stage 4, this is when we begin to tone those liners. We're getting ready to ship them or to transplant them. Again, we're going to want to use supplemental lighting, 70 to 120 micromoles, and we're going to want to maintain a daily light integral greater than 12 moles of light. Now, in some parts of the country, it's going to be very difficult to maintain 12 moles of light, because even with supplemental lighting, you may only be able to achieve 10. But as we tell most growers, the higher that daily light integral, the higher quality of crop that you're going to be able to produce, and the faster that you're going to be able to get that crop out of the greenhouse. At this time point, you're going to be able to increase your light intensity anywhere from 500 to 800 micromoles per meter squared per second. Now here's some work with New Guinean patients. Oftentimes we consider New Guinean patients maybe requiring less light, but as we can see with this photograph was taken 16 days after the cuttings were stuck. So we have daily light integral ranging anywhere from 1 all the way up to about 11 moles of light. And when we use supplemental lighting, in this instance high pressure sodium lamps, we see a very large increase in root dry mass, and that basically tells us that we can produce a rooted liner of New Guinean patients in just a little over 2 weeks, where if you're not utilizing supplemental light and have very low daily light integrals, it's going to take you nearly 6 weeks. Here's another example. This is a species that's very responsive to an increase in daily light integral. This is Acknowledgements. So here we have ranges anywhere from 1 all the way up to about 12 moles of light. Again, we see our root dry mass increase dramatically with that increase in daily light integral, which again, we're going to be able to produce a rooted liner much faster when we use supplemental light. And here we have an example of a species that's not as responsive to daily light integral, where when we look at that root dry mass, we can see that when we're at a daily light integral of around 6 moles of light, we basically see very little increase beyond that, indicating that this particular species may not necessarily be one that you would use supplemental lighting on. So one question that we often receive from growers is, well, there are obviously now LEDs on the market. How do cuttings respond in terms of rooting? And so here we have an example where we have basically, again, supplemental lighting from high pressure sodium lamps, or increasing blue. So anywhere from providing 100% red light up to providing 70% red light and 30% blue. We can see with impatiens and petunia and even geranium, we found that there were no statistical differences in terms of how the cuttings rooted, so they didn't root any faster under LEDs compared to high pressure sodium lamps. So some of the results or recommendations that we can provide for rooting, at least for ornamentals, is that LEDs are comparable to high pressure sodium lamps in terms of providing supplemental light for both callusing as well as rooting of annuals and perennials. We have found that the finished plant quality, so basically when you take those cuttings into a common environment and finish the crop, again, there's no significant difference in terms of time to flower, height, or overall quality, whether they were propagated under HPS or LEDs. So below we basically have a table indicating our recommendations in terms of daily light integral, as well as root zone temperature, as well as air temperature and the vapor pressure deficit during propagation of young plants. So now we're going to move on and talk about supplemental lighting during plug production. So again, this is for seed. So previous research here at MSU has recommended, again, very similar to rooting of cuttings, providing anywhere from 70 to 90 micromoles of supplemental light during stages 3 to 4 to achieve a DLI of 8 to 12 moles. So we find that when you provide supplemental lighting for plugs, you're going to see increased rooting. So again, you're going to reduce the production time of those plugs. You're going to see an increase in stem diameter, which is obviously going to produce a sturdier plug and more branching. Oftentimes when these young plants are grown under high pressure sodium lamps because of the additional heat, you're going to see that they're going to flower earlier upon transplant, which can, for some growers, be a good thing. For others that maybe want to bulk up the crop, they may have to use Ethifon to abort those flower buds and get that plant to grow a little more.
Roberto, there are a couple questions that have popped up, and I thought I might ask them right now.
Sure.
They're probably a couple slides ago. The first is the daylight integral for propagation of sun plus duo light of 10 moles per day, does that mean 10 moles only from supplemental lighting or from both sources?
From both sources.
Okay. And then the next is, in terms of root growth, HPS and LED fixtures may be comparable. How did you also look at the difference between light blockage of HPS and LED?
So in terms of those recommendations, it was basically just the quality of the crop in terms of root dry mass, time to flower. We did not necessarily look at how much sunlight was blocked by the high pressure sodium fixture compared to the LED. So when we did a lot of the initial work, we utilized experimental LEDs or LEDs that were blocked out a lot of the sunlight. Now, obviously, there's fixtures on the market that are comparable, or in terms of, or even produce less shade than a high pressure sodium lamp.
Thanks.
So we have also found that when the ambient daily light integral, so this is from sunlight, is quite low, less than 7 moles of light, and let's say a grower uses supplemental lighting from an LED fixture providing 10% or greater blue light, we can find that with certain species, Petunia being one of them, that those plugs are going to be more compact. And what I mean by more compact is that they're going to have a reduced leaf area and stem elongation. So the need for growth regulators could be potentially reduced or eliminated. We also find that when you have greater than 10% blue light, you will see an increase in chlorophyll. So those plugs are going to appear greener, and you're going to see an increase in anthocyanins. So if it's a species that has red leaves, you're going to see more intensity in that red or purple leaf color. So here's some work that Erik's lab did a few years back, and basically it shows how plug quality increases with an increase in daily light integral. So a daily light integral of 6 compared to 16, we see that those plugs are slightly more compact, but more importantly, we see that increase in roots, which means we're going to be able to ship out that plug tray or transplant that plug tray much faster. But obviously, being able to achieve a daily light integral of 16 moles is going to be quite challenging in a northern latitude. Now, if you're located in Texas or Florida, that might necessarily not be as difficult. Do you have another question, Erik?
Yeah, so I'll take it here the next. We've already answered that one question. Which brings us to another. And so in an ideal world, greenhouses are filled with lighting fixtures, and they can deliver light on demand in their entire range. But then, of course, practicality hits, and a lot of growers only have supplemental lighting in certain portions of the range. And so the question was, if you cannot light your entire crop, your entire seedlings at least, at what stage of growth do you get the greatest benefit? And so with some colleagues a while back, we did some research specifically looking at where is the greatest utility of supplemental lighting. And so in this case, we took Petunia and Pansy. The crop times for these were either 27 days or 33 days. And so that's basically the time from germination until we deemed the plug to be ready. We never in these types of studies, we typically do not apply growth retardants, and so the plants grow rather quickly. So we divided these crops into 3 stages, into thirds. So for petunia, a stage was for 9 days, and for pansy, a stage was for 11 days. And then we delivered 7 different types of treatments. So the first was LLL. That's where we had a low ambient daily light integral, and the plants did not receive any supplemental lighting. Alternatively, other treatments included supplemental lighting during the first third, the middle third, or the last third, or during the first 2/3 or last 2/3, or by comparison, the seedlings were lighted the entire time. There was basically, from the time of seed sow, you can see comparatively, we're starting the study. Much of that first stage is basically where the seedlings are emerging. And so I misspoke earlier, we actually started the treatments at seed sow. They're emerging toward the middle to latter third of the first stage. And so during that first stage, we're often lighting just some bare soil. And then you can see the end of the third stage, we took these seedlings, and like we do in many studies, we then carry them over and transplant them to see if there's any residual effect of the lighting treatments during the plug stage on subsequent finished plant performance. Here's a slide that was taken 27 days after seed sow. These are grown at 68 degrees Fahrenheit. And basically, as you go left to right, you can see a corresponding increase in supplemental lighting. So on the far left, there's no supplemental lighting. On the far right, there's supplemental lighting the entire time. And then you can see the H represents the relative period of time in which there was supplemental lighting delivered. I think looking at the pictures, you can see pretty good what the results indicate, where first of all, the supplemental lighting has a benefit, especially as you light during the last 2/3 or the entire time. Of course, we want to take more than just pictures. We start collecting data, measuring what is the shoot mass, and we often measure shoot mass because it's a good indicator of total plant growth. So here for pansy, this is after 33 days. You can see that you have a tendency of increasing shoot mass as you increase the amount of light, or at least if you're lighting during the last 2/3 of the period of the plug production period. I should also point out that if you could only light 1/3, if we light or look at the plants, if they were lighted only the first third, there's basically the same sort of mass as not lighting at all. Whereas if you lit during the middle or especially the last third, you see not only better rooting, but also a greater shoot mass. And then looking to see the residual effect, indeed that the plants that were lighted, especially longer, did flower earlier. It wasn't a huge number, but it was typically 3 or 4 days, which shows that there is a residual effect or a benefit of a plug that was lighted versus one that was not. Or conversely, or similarly, you could say that a plug that was grown under a high light integral will flower earlier than a plug grown under light limiting conditions. Roberto and his group have done similar work, in this case with petunia, and they stripped off or removed the substrate so you can see the root system. When these were then grown comparing under high pressure sodiums or red and blue LEDs at the same intensity of 70 micromoles, in some cases, especially when the daily light integral was low, there was a bit more of a compact plant under the red and blue LEDs compared to the high pressure sodium. And regardless of the light source, you can see a clear benefit where the plug has a thicker leaf and the rooting is much more developed than the plants that are not lighted. And then similar results here with zinnia. Again, you can see maybe a small impact of the fixture type, the red and blue LED, maybe a little bit more compact, but root growth is similar, whether it's from high pressure sodium or red and blue LEDs, and much better than under ambient light without supplemental lighting.
Erik, let me interrupt you for a question now. We got a question from the audience asking, is it best to use HPS, do the heat generated, as opposed to the LEDs?
So when we do, in a little bit, we will talk about decisions of HPS versus LED, and it's highly situational. some growers do like the heat that's emitted from the fixtures, and it will indeed increase plant temperature by typically 2 to 3 degrees Fahrenheit. So that might be a side benefit, but one could also argue that that isn't not an efficient way of increasing plant temperature, that using electricity to create heat is not as probably cost effective as just increasing the air temperature using another source like natural gas. There's a question on the root growth of the LEDs and whether there was a difference in the root growth under LEDs versus HPS. Roberto, you recall a difference?
Only in a very few species. So I would say generally we don't see a large or a significant difference between plugs or cuttings in terms of root growth and between LEDs and HPS.
And in our research that we're not going to talk about today, but similarly, we've not seen any meaningful differences in root mass if the supplemental lighting intensity is the same.
Okay, so as Erik indicated, oftentimes we do see that growers can have challenges in terms of telling the difference between a supplemental or photoperiodic lighting. And in the last few years, we've seen several young plant growers utilizing low intensity LEDs, as we can see in this photograph where the fixtures are circled in yellow. So the question is production time reduced compared to plugs grown only under natural light or no electric lighting? So basically, let's say you're a plug producer and you've never used electric lighting and you've now started to use these low intensity photoperiodic LEDs. Are you going to see a difference in time, in production time? So here's an example of some of the fixtures of photoperiodic lighting fixtures that are available on the market. They typically have red, white, and far red light. And we can see another example where a young plant producer is utilizing those lights in some instances up to 24 hours a day. So the objectives of this study were basically to quantify plug quality as well as production time under various treatments. So there are several treatments. I'm going to try to go through them quickly just because of the sake of time. So with the treatments, we basically ran high pressure sodium lamps or high intensity LEDs continuously for 16 hours or on an instantaneous threshold, meaning that the lights were basically provided a 16-hour photo period, but during the day, they were only on when light intensity outdoors was below 400 micromoles. Our other treatments were either 16-hour or 24 hours of low intensity lights utilizing these LEDs that contained far red or they did not contain far red. And then we compared those to basically plugs that were grown under no electric lighting. So here are the results for petunia. In the top figure, basically those were all plants that were grown under supplemental lighting or no lighting, and then those at the bottom were grown under photoperiodic lighting. So now let's look at those that were grown under high pressure sodium lamps. In the first example, we basically provided 70 micromoles of light for 16 hours continuously. So if it was sunny out, the lights still ran. However, under threshold lighting, we provided a slightly higher intensity. So we went up to 90 micromoles. And again, those lights were on early in the morning and late in the evening, and only on during the day when basically the plants needed that additional light. We also had the same exact treatments under LEDs that provided red, white, and blue light. So when we compare the shoot growth of the petunia, basically between high pressure sodium and LED, we see a very large difference in shoot dry mass, right? We see almost a 50% reduction in shoot dry mass. So those cuttings are obviously, those plugs are obviously much more compact. Now let's look at those plugs that were grown under photoperiodic light. We see that the shoot dry mass is very similar to the control, so basically no lighting. However, we do see a large increase in leaf area. Now let's look at the roots. Obviously, this is probably one of the most important things with a plug or a cutting because we want to produce a rooted liner or a rooted plug tray. So we see that statistically, there was no difference in root dry mass between plugs that were grown under high pressure sodium or under light emitting diodes, whether we had a threshold or ran those lights continuously for 16 hours. Now look at the root dry mass of those petunia seedlings that were grown under photoperiodic lighting, very similar to those under no light. So that shows us that basically that low intensity lighting, it's not providing enough light for photosynthesis, therefore we're not seeing an increase in root dry mass. We then transplanted all of these seedlings into a common environment. So we had an air temperature set point of 68 degrees Fahrenheit, and we grew them under a 16-hour photo period with high pressure sodium lamps. So the treatments that we see here are basically the treatments that these seedlings received during propagation, and now they're in a common environment. We can see time to flower. So petunia, being a long day plant, it took about 31 days to flower. However, when we grew them under high pressure sodium lamps, so high pressure sodium lamps have a little bit of far red light, we see about a week to 10-day reduction in time to flower. Now with these LEDs, they had red, white, and blue light, no far red. So we see a very similar time to flower compared to no lighting. And with the photoperiodic lighting treatments, we can see, again, a reduction in time to flower, especially when we have that far red light. So with this study, basically, again, it validated our results from previous studies when the ambient daily light integral, so again, this is sunlight alone, is less than 7 moles, and you're utilizing LEDs for supplemental lighting, or when your supplemental lighting contributes to, let's say, 40% or greater of the total daily light integral. In some species, such as petunia, you can see a more compact seedling. They're going to have smaller leaves, in some instances, more roots, and an overall greater quality. We have found that plugs under supplemental lighting are, again, depending on the species, can be marketable anywhere from 2 to 3 weeks earlier than if you don't provide any electric light. Of course, this is going to be more common in a northern latitude. And by using the threshold lighting, basically we were able to operate the lamps for a much reduced time, and obviously leading to energy savings, and we saw no statistical difference compared to running those lamps 16 hours a day. Now when we look at those plugs that were grown under photoperiodic lighting, the quality was very similar to providing no electric lighting. We did see that by providing photoperiodic light, we saw stem elongation because we were running those lamps anywhere from 16 to 24 hours a day. So we're obviously providing additional far red light, so we're going to have larger leaves. And for those growers who are utilizing them, basically we're seeing an increase in leaf area. So there's the perception that the plugs are finishing faster, but really when you look at the roots, that's where you see that there's very little increase to no increase in root dry mass. Plugs that were grown under photoperiodic lighting were marketable approximately a few days earlier than those under electric lighting. But again, I think this shows the value of using high intensity supplemental light.
Roberto, there's a question.
Okay.
Do you think root mass development in cannabis and petunia could possibly be similar?
You know, I think when we think of plants, a plant is a plant, and you know, it doesn't matter whether it's an ornamental, a vegetable, you're going to see very similar results.
Okay, thanks. So the last component we'll talk about, our time is running short, so I'll go through this a little bit quickly, is to address the question of, with supplemental lighting, do you go with HPS or LEDs? And as you'll see, it's very situational. So these are just among the major considerations. There are certainly going to be some that we probably won't mention today. One of them is the amount of electricity that's available. Do you already have enough electrical supply to add the fixtures, or do you need to bring it into your facility? That can have a substantial impact on your decision based upon how much energy you need to bring in. The cost to purchase and install fixtures, including whether there are rebates available, the cost of the electricity and how many hours the fixtures are run, the lamp efficacy or efficiency, which is expressed in the photons per joule, which is in the unit of micromole per joule, And I will mention that I'm going to be going through many of these in a little bit more detail here in a minute. What is the longevity of the fixture, and is there any maintenance that's needed? What about the light spectrum and considerations, first and foremost for plants, but also considering people? What about the uniformity of the intensity delivered? Can we get a better uniformity with one fixture type? That's possible. And then, as mentioned previously, the fact that plants under high pressure sodiums are typically 2 to 3 degrees warmer, which in many cases can be desirable, but may not be an economical way to increase the temperature. So looking at a little bit more detail for these, one of the first steps in addressing this consideration is to work with a lighting company or a lighting supplier and work with them to obtain a customized light map and price quotation for your specific facility. Companies will now readily do this. You basically give them the dimensions of your greenhouse, the hanging height that's possible at your facility, in other words, the distance between the fixture and the growing area. They should be able to give you details for a specific light intensity that you want to deliver. They should give you details about the light spectrum, and you might communicate any preferences you have. They should be able to give you information about the efficacy of the fixture, the expected lifetime, and whether there are any warranties. And then something that's sometimes overlooked is to think about how easily the different fixtures are installed. Some of them can be connected from one to another and are more rapidly installed and more easily installed than ones that have their own power supply that needs to be hung separately. This is just an example of a lighting diagram. This is actually for one of our greenhouse sections at Michigan State, where we asked for an average intensity of 90 micromoles. And for this rather narrow greenhouse, you can see it's only 14 feet wide. This is actually half of one greenhouse for illustration, but you can see what they predicted to be the placement of the fixtures and the average intensities over the surface area. And this is a reasonably good uniformity, and we typically say that if you can get within 20% variation in light intensity, that's generally acceptable. I mentioned this about electrical supply. So do you have enough electricity already to your facility, or do you need more power? And of course, bringing power into your facility can be very expensive. So consider those costs when you're looking at how much power you need to bring in. And of course, now with the more efficient LED fixtures, you will not need to bring in as much power as with high pressure sodium. Question about whether there are any lighting layout programs that we can recommend. Actually, I have no experience with the lighting programs. These are basically software tools that the lighting companies use, and they have basically files that are specific to their fixture. And so it's usually proprietary information, and it's really something that lighting companies are set up well to develop, and it's hard for someone not in the industry to develop these lighting layouts. In terms of lighting distribution uniformity, again, that's not something that we measure. That's something that the grower would measure, the lighting company would measure. Now, we do check to see what the uniformity is, just taking a quantum sensor and moving it around on the bench. And we will often measure and report that in a publication. This is a photo that I took at Rutgers. It's an integrating sphere that AJ Both has. It's basically the only effective tool, or the most effective tool, that professionals can use to measure the total output of a light fixture. It's a very expensive piece of equipment, and it takes considerable expertise to operate. And so this is not something that, well, I should say very few academics actually have one of these, but most lighting companies do. And so a fixture is placed inside, and the total amount of light emitted from the fixture at a certain temperature and with other standards is measured, as well as the amount of energy that's consumed to emit that light. And I'm sure if you have more questions about this, AJ Both would be happy to address those. So looking at fixture efficiency or efficacy, just an example that if a fixture emits 500 micromoles per second of photosynthetic light, and it consumes 200 watts to emit that light, you can do the math and it equates to 2.5 micromoles per joule. So that's how we get these efficacy values. And of course, the more light that is emitted per joule, the greater the value, and therefore the more efficient the fixture. These are some data points from publications from academics. Some of these are rather old data points, but some of them are from last year. They are just to give you some examples of data points that really have not changed much for high pressure sodium in the last 5 years, but are changing rather dramatically for LEDs. So at least in Michigan, and actually many commercial greenhouse operations we visit for ornamentals, we'll typically have a 400 watt high pressure sodium, which has a photon efficacy value of 0.9. It's obviously a very low value compared to a double-ended fixture. You can see is almost twice as efficient. But then now when you look at LEDs, again, some of these will be out of date, but they are in many cases higher and substantially higher than the double-ended. And there are now fixtures on the market that are advertising of values of 3 or even above that. So the number is changing fairly rapidly. And is improving, especially for LEDs. Thinking about the spectrum and the distribution of the radiation, many of the horticultural fixtures emit a pinkish or a purplish light, and that's because they primarily or exclusively are composed of red LEDs and blue LEDs. And so combined, they emit this purplish color of light. There are, however, examples of companies that emit or that have primarily white LEDs that emits a nice light from a human perspective. There are also fixtures that have red and white combined in different amounts. And then some fixtures or some companies have fixtures that combine red and white as well as far red. And then the question is, what is the desirable spectrum from a human perspective, but especially then also from a plant perspective? So white LEDs are really a blue LED with a phosphorus coating that scatters the light into longer wavelengths. We generally recommend supplemental lighting. Fixtures emit somewhere around 10 to 20% blue. There may be some applications, however, where a higher blue percentage may be desirable, especially if one is looking to increase the concentration of secondary metabolites or anthocyanins or other specific pigments that are increased as a result of blue radiation. Something else to consider in terms of the distribution is basically how much of the light that is delivered from supplemental lighting reaches non-growing areas. And so if you are able to tailor the spectrum, or excuse me, tailor the fixture emission pattern so that most of that light is down toward the crop, you'll have less that's lost to walkways or sidewalls or other areas that are not meant to be lighted. And then people. Some people find that purplish color to be a little bit unpleasant. Some think it's rather unpleasant. And so if people are working, especially at night, consider fixtures that even emit some white light. It doesn't take a lot of white to create a more pleasant working environment. There is a temptation to find a fixture that is cheaper. Probably no surprise, we're all looking for shortcuts, but there are often negative consequences with fixtures that are not meant for horticultural applications. And so people may be tempted to look at fixtures that are currently being used for other applications, such as at a gas station or for street lights or parking garages. In many cases, these are not designed or appropriate for horticultural applications. They may not be sufficiently damp-proof. The uniformity is often not considering a greenhouse area, but oftentimes the actual amount of light emitted from these fixtures is much lower than what you'll get in a horticultural fixture. They also typically have a lot of shading. So in a greenhouse situation, you want a fixture that minimizes shading of sunlight. So here's just an example. These were kind of an older generation LED, and to get a meaningful intensity, you can see it took a lot of arrays overhead to get the desired light intensity. Operating costs, obviously cost is the major determinant about whether you invest in an LED or an HPS. What is the purchase cost, the installation cost, and then the cost to operate them. And so operating costs can be estimated if you know your electricity rate and about how many hours you anticipate running the fixtures each year. So a typical greenhouse grower for ornamental plants growing propagation materials might light around 1,000 hours per year, maybe up to 1,500 hours per year. It's rarely more than that, unless they are growing crops year-round. So in other words, starting in the fall all the way through the spring, or if growers are even lighting for a longer period of the year. And you can see sometimes growers using lights as much as 3,000 to sometimes 4,000 hours per year. Impact of temperature on heating. I mentioned this, that plants are typically a little bit warmer under high pressure sodiums than LEDs, but it's a relatively inefficient way of heating the crops compared to other heating methods. In some situations, there are rebates available for more energy efficient fixtures, especially if it's to retrofit an existing installation, and this can dramatically influence the economics of a lighting decision. I do say that these seem to be less available now than a few years ago. However, there are examples even going on today where utility rebates are interested in providing, utilities are interested in providing rebates if you install LEDs compared to a more energy consuming fixture. So calculating the costs, a lot of companies have developed spreadsheets and can help you estimate a return on investment and the payback time for an LED versus an HPS. I think these are very helpful tools. What's important though is to scrutinize the assumptions. And sometimes the assumptions are not appropriate for your specific application. So I'm going to put up here just an example of a spreadsheet from a company developed several years ago. It's out of date and I think has been modified substantially. But to scrutinize the details and make sure, for example, that the operating hours is correct for your facility. So for those of you who can squint your eyes and have good eyes can see that in this case, the assumption was to operate fixtures for 3,650 hours. That might be appropriate for a tomato grower who lights most of the year, but it may not be appropriate for a grower that lights seasonally, such as a propagation grower. So these are helpful tools, can help you make decisions. Again, making sure that the inputs are appropriate for your situation. So with that, I know I went through these last slides relatively quickly. I want to share some acknowledgements of companies that we have been working with over the years that have made in-kind contributions or donated specifically to our program, as well as granting agencies that have subsidized or supported our research. We certainly thank them because without their contributions, we would not be able to do the research that we've been doing. A couple resources for more information. Roberto and I edited a book with many of our distinguished colleagues who wrote chapters on light management in controlled environments. It contains 18 chapters written by 20 different people. The target audience is growers and lighting representatives, as well as useful for college students. And it's available in print and digital format through Amazon. We also maintain a website that's basically a compilation of many of the resources that we have developed, especially articles that we have written for the trade magazines, and that's the URL. It's a little bit long, but I think if you type in Light Management Michigan State or something like that, you will be directed to this page. And then a couple closing slides for the webinar series. Eriko, I don't know if you want to take it from here.
Sure, thanks, Erik. Yeah, let me just, let's do some questions. We can leave it right so people can be aware of the next webinar series. And if you can click one more, then they can see the whole. We got a few questions here. I think we have a few minutes to answer some of those. So you can see the questions as well, right, Erik?
Yeah. Regarding, are there any OSHA requirements regarding color of light? That is a question I do not know, other than blue light and of course UV are wave bands that we need to be careful about. And so there are some guidelines. Eriko, do you know specifically?
No, I'm not aware of that. The requirements on color of light, I don't think that's the question, but it could be relevant. So the DLC has now a certification for horticultural lighting fixtures, and they have some minimum amounts of light that you need within which wave band. So within blue, green, red, far red. So they make a few recommendations there. It's worth taking a look. But that's more for lighting manufacturers getting those fixtures qualified for rebates. It's not really health or safety, anything like that.
Right, right. But certainly if you're using a fixture that emits a lot of blue, you know, at a minimum, you don't want people to look at the fixture, and you may want people to wear protective eyewear. The next question is, if we talk about supplemental light for crop production and not cuttings, will 200 micromoles per meter squared in second be sufficient, delivering about 9 moles additional per day? So that will so it depends on the crop and the quality. So that would be a sort of intensity that we would see by a tomato grower. That's going to be at the upper end, maybe cucumber, maybe pepper. That is enough to get a meaningful improvement in the quality of the crop, as well as to increase the crop yield. In fact, it's rare that I see supplemental lighting intensities higher than that, although I'm sure they're out there.
And cut flowers would be another example that you could potentially see those light intensities.
Can you share the link for the last form? I'm not sure if that refers to...
That was a table that you show calculating the ROI. That's when the question came. Before that, Erik, the table with the ROI, hours of function of the light.
This one?
That one, the question came right there.
Okay, so this is not publicly available. It's basically and I don't think it was a finished product. It was basically a work in progress that showed things to consider. So unfortunately, I don't have this other than a snapshot, like as a photo.
Chris Morgan then has a question, which is, what is the optimal amount of light needed for plug grower? Early, you had mentioned 400 micromole per square meter. Is that a good number to shoot for?
So the 400 micromole, that's basically when we measure 400 micromoles per meter squared per second, that's when we shut off our supplemental lighting. So that might have been a little bit of a confusion there. It's now the light intensity is going to vary based on the stage that you're producing that plug. Same thing with the cutting. So initially, you're going to want to have lower light intensities, and you're going to increase those light intensities as the stage increases.
So Roberto, could be a good recommendation could be to follow the amounts you indicated on your initial slides. I think you had 4 stages.
Exactly.
Light level. So that is a good starting point, I believe, right?
Correct.
Perfect.
And I would add to really the daily light integral is a more important metric to track, and not just an instantaneous value. So if you're already getting 10 moles of light in your propagation facility, there's probably no good reason to install high pressure sodium or LEDs. Quickly, does it matter if your DLI is continuous, such as 16 hours consecutive on versus 8 on, 8 off? The answer is simply no. Yeah, it's total amount of light, and whether you deliver it over 16 or 8 hours or 8 on, 8 off, it doesn't matter.
We do have 2 other questions, but we are about time here. It's 3 p.m.
Okay.
So yeah, I want to respect everyone. I can follow up with the 2 questions that I have. I can share some information on the email. I would like to thank everyone for participating. I would like to special thanks to Erik, Runkle, and Roberto Lopez. Thanks for giving the webinar. It was very interesting. We got some good feedback here, good questions. I really appreciate the time. And I will follow up with all of you. I can share those questions that we received today. So if anyone has anything specific, you can just outreach to me and I can make these connections. Thanks so much, Erik. Thanks so much, Roberto. I hope you have a good day, and thanks everyone for joining the webinar. Any final statements or any notes?
No, appreciate the opportunity. Thank you.
Perfect. Thank you so much. Have a good day, everyone. Bye-bye.